Sweet. I think we're live. Okay. So we are back from the weekend and going to attack some problems today. I won't be able to stream terribly long, so I may just be able to get through my Anki. But regardless, it's going to be good. I recently read a essay that was like insane. So I think, yeah, I'll just put that in the chat. I think things are gonna be changing. So I think I'm gonna be full diving into Gwen and yeah, highagency.com by George Mack. I think I'm gonna be full diving into Gwen and going hard on that. So I'm pretty excited. Anyway, so we're back to calculus, and I think we'll do some practice. Well, we're going to do Anki first, and then we'll probably do some practice problems if I have time. I'll probably be ending in like 25 minutes or so it'll actually be pretty short. So maybe I'll be able to list out all the like categories of problems that I'll need to practice, because right now like I have a pretty good conceptual understanding for most things in calculus 1, and I haven't practiced much, so there are variations in problem types that I probably wouldn't be able to do. And then yeah, so I just need to run through a few of those, and then I think we'll be, about there. So, okay, so I'll just pull up this. Go ahead and switch the screen share. I did not do my Anki today, unfortunately, or the past couple days, but all is well. Okay, Euler's number. This is it's like 1.2, I believe, ish, and this is used for decay and growth and like natural processes. Oh, 2.7. Okay, I think I'm actually gonna redo that though, and then and I might want to look into more as to how it's derived. But for now, that's fine. Inflection points. So here you take so an inflection point is when a function goes from convex to concave or vice versa. And they're found by taking the derivative of the derivative, which is the second order derivative, which would represent the rate of change of the slope. And so if you have a rate of change for a particular thing and it inverts, right? So say I'm like moving along, I'm moving along, I'm moving along, and then actually that's not a, well, yeah, that's reasonable. Anyway, so we can think about like the rate of change as this occurs across this function, and also we can think about how the rate of change changes, right? And there's a particular point where if we take the instantaneous rate of change, it's going to be 0, right? And so in this situation where our function's really nice, it's like a nice little bell curve, it's clear when like it's at like its like highest point there, right? But if we were to go like this, so it's clear like here, we're like switching up. But say we're going like that. Oh, let's see. Okay. So at each of these points, it's going to be 0 slope, right? If we take the instantaneous. But so we could use that, but using the second order derivative, only in situations where it's like a sort of a sine wave kind of thing, you could use merely the slope. But for like other functions, like say I have one that like goes up like this, obviously these points aren't 0, but the slope of the slope is 0 at these points, because the slope growing and then the slope decreasing, right? Slope growing, then slope decreasing. So at each of those points where it grows or begins to grow or begins to decrease, or pretty much when it passes 0, you know that you have an inflection point. And so that's how we find it. That was long-winded, but okay. Lagrange and Leibniz. Lagrange is okay, I think the Lagrange one is closest to the Newton, and that's the Newtons, and Lagrange is the one with the little notation with the little apostrophe, and then Leibniz is and so Lagrange is merely describing the derivative, and then Leibniz is focuses more on the rate of change. So I think it's dy over dx for Leibniz. Yeah. Leibniz, dy dx, Lagrange. Yep. Perfect. Okay, dy over dx. Emphasizing rate of change. How do you integrate using Riemann sums? I could talk through it, but I'm not sure I know. I've never done it before. But you take sort of the rectangles. So a integral, definite integral is one in which we're finding the slope, the volume under the curve, right? And so we can think of the volume under the curve as a set of rectangles of varying heights that sort of match up with the curve line. And so with this one, you just sort of figure out a particular how specific and how fine-tuned you want to be with how close you are to the approximating it. So the more rectangles we use, the closer we are to approximate it, the less rectangles, the less, right? And then you just would add each of those up, sum them up, and then yeah. Okay, yeah, so we're dividing the intervals into the equal width, and then we're approximating it by summation. For the mean value theorem, why do we need to be continuous on a closed interval and differentiable on an open interval? So continuous on a closed interval means that it's including those two endpoints. We need to be continuous because if we have breakpoints, so the mean value theorem states that for, we'll say, this, say there's a point here and a point here. Let's see. A point here and a point here. So we have the cosecant line, and then we have the tangent line. And so what the mean value theorem states is that there's a point on this line where the slope of the tangent line is equivalent, or the slope is equal to these 2 points. And we have to be continuous from this point to this point, because if we have a break, then it could be the case that the slope of the tangent line, or the tangent line point, was supposed to be there, but it wasn't. And then it needs to be differentiable because we need to be able to write the line at some point. Like if this for some reason isn't differentiable, then we can't guarantee it because we can't find the slope of the tangent line. So at all points along the line, and it's on an open interval because we don't need to check the slope for these, I believe. Let me just double check. I think closed interval is including, and open is exclusive. So we'll just double check that real quick. Includes endpoints. Yep, perfect. Okay, local extrema. Okay, so I feel like I remember hearing about this one, and then so this is how do you find local extrema in calculus. I remember, I feel like I remember learning about this, and then it became clear to me why this was the case. So I'm just going to expend some effort into trying to figure out what it is. So for local extrema, we're going to be finding we're going to be finding like a high point for ooh, yikes. A high point for a particular area. Or a low point for a particular... I don't actually know if that's exactly the case that we're looking for. Anyway, So if we're going up here, and I'm going to look at two different, for what I'm doing here, expending cognitive effort here will help me to really ingrain this deeply. If I'm able to spend some effort and then actually retrieve the answer, it's likely that I just like won't forget, right? Like you could just look at the question, right? So there's that. So local extrema would be, I'm not sure what by extrema, if they mean like for a given value x, the highest proportionally value y. So for this one, like for this given value x, it's proportionally, or this given value x, it's proportionally higher to this value, or the output y is higher in proportion than this one because it's at like the same level. So I would identify this as a local extrema in this case. If we maybe took it from like here to here or something, that seems like the local, phenomena. And maybe in terms of like how this could also be like a different type of local extrema. Actually, yeah, I'm not sure. So I think, okay, so it's not just a matter of going concave to convex. So we know it's not just the second order derivative. You could hypothetically just like for a given point. Well, yeah, I'm still not sure what is meant by extrema, because I feel like it's like it may be the case that, so say we have 1 and 2 and 1. So like for our input 1, we have much higher output than we do for our input of 2. Like proportionally, like we have 1 unit of input here and we have 2 units of input here, and we still get around 1. So this could be thought of as an extrema, but I'm not sure. So we'll just look at this one again. Find the derivative f of x. Solve f of x where it equals 0. Okay, solve for... So when our slope is 0, we're at critical points. Okay, so when we level off, it's not about the proportionally per se. It's about when maybe we're updating or changing, like in an important way. So that would be like right here. Let's see. Right here we're updating. If this one like sags down a bit, we'd probably have, or actually we would have another point there. And so those would be thought of as extrema, but I guess they're extreme in, okay. How do you find the local extrema? Okay, so, use the second derivative test. Okay, so this, okay, so these are critical points. Okay, so local extrema are critical points, minimums, and maximums. Okay, I think it's reasonable that a critical point is that when our slope changes from negative to positive, because each time, if we have a continuous function and it's not just like a straight line, each time our slope hits 0, we're like something's happening there, and so I think that would be called a critical point. And then if we use our second derivative test, when our so this is the rate of change of our rate of change is greater than 0, we're at a local minimum. But if it's less than or equal to 0, or no, just less than 0. So if the result of that is less than 0, we're at a local maximum. Now, I'm actually unsure of how that is. Because I would assume that okay, so maybe you could say that when it's greater than 0, so when our rate of change is approaching 0, we're at like a point of change. And so if it's coming from the negative and approaching 0, and then like inverting back to positive. So if our rate of change is slowing down, and then we have like it starts to like go the other way, right? It goes positive. Then at the point at which it is the lowest, so it would be coming down. I think at the point it hits 0, it would be probably a minimum. So we're going negative to 0. So perhaps like this is saying that when it just, so what I'm concerned about is like, it seems like for our local minimum, well, okay, actually, no, I think this is reasonable now. So so say this is our second order function, second order derivative, and we're going like this. At this point here, so this is our rate of change, or the mapping of our rate of change. At this point here, we're probably at our lowest point, right? Because our rate of change is going inverse. And then at this point, it begins to go back up. And then this is when it is at our like highest point. So I guess you could be saying that like, just, let's see, this is the local minimum. So maybe they're defining that like just past this is our local minimum. And just before we start going negative is our local maximum. I don't understand why they, right, because, okay, let me describe. So if it's not, for me, it seems like it's not that we're talking about greater than or less than. I don't think it's not reasonable for me to be greater than or less than for the local minimum and local maximum. And obviously I'm going to dive in and figure out what the answer is, but I'm trying to generate a hypothesis here. So I would be less surprised, or it'd make more sense to me if the local minimum was the 0 point, right? Because for our rate of change, or the 0 slope for our rate of change, because say we're going down, it would be right here. So we're going to hit 0 slope at this point and 0 slope at this point, right? And so maybe this is a way of defining that, like, because we go negative right here on this side for our slope, and then we go positive. So we're negative here and then positive here. And this is saying that the second order function, or the second order derivative, is greater than 0. So what it seems to be saying is that we're like eking just past the lowest point to be right here, because this is where it would be greater than 0. And then inversely, this is saying when the result of this function is less than 0, which would be just after this, because this is negative here because our slope is going down, right? And so it seems odd to me that we don't, well, yeah, it just seems odd to me that we're saying less than or greater than here, especially because yeah, I would assume that it's actually at 0 that our minimum and maximum values are found. And then additionally, yeah, so I think I'm just going to ChatGPT this. Let's see if I can tease out any other insights. So this is when it's greater than 0. And then additionally, if this was wickedly high, like if our f of like this function was really high, it means we're like increasing in slope, right? And then as it tapers off, it goes back to 0. And so is greater than 0. Yeah, I don't think I can move any beyond what I have so far. It doesn't make much sense why it's saying greater than 0, because I think it should be 0. Yeah, I'm not sure. Okay. ChatGPT. Okay. Could you tell me about local extrema within Calculus 1? Question mark. I'm having a hard time understanding when we're finding the minimum and maximum why it is the case that we take the, or rather for the minimum, why is it that we're looking for the second order derivative is greater than 0, and then for the maximum we want the second order derivative to be less than 0. It seems like for the minimum and maximum points they would actually be at slope 0, but they would just be at different places. So the minimum would be the minimum where it's at slope 0, because that's when it goes from, I don't know, convex to concave, or vice versa, depending on how you look at it. And then at the maximum would be the maximum point before like the inverse occurs. So if you could describe that. Okay. Okay, so when we talk about local extrema in calculus, we first look for points where the first derivative is 0. Oh. Okay, so we first look for where the derivative is 0. So where the rate of change is 0. Okay. Okay, I think that makes... Oh, okay, so I thought the critical points were a separate category of extrema and not preparatory to calculating the minimum and maximum. Okay. However, not every critical point is a minimum or maximum. A point may also be a saddle point. The second derivative test helps us distinguish between these possibilities by giving us information about the curvature of the function at that point, a local minimum. If the second derivative of a critical point is greater than 0, oh. Okay. Okay, so the idea that I was missing was that we're looking at the point at 0, these critical points. So I think I'm going to add this to my study here. I do think I already have this. Let's see. Local extrema. Yeah, okay. So I already have that. Right now I'm just going to remember this. So we'll just move past this. So this is 2.4-ish. And the function for for generating this is 1 plus 1 over n in parentheses to the n. 1 plus 1 over n in parentheses to the n as n approaches infinity. And then 2.7. Okay, I'm close enough there. We'll get it more as we interact with it. Lagrange notation is when we use the prime. Yep. Open interval is when we is exclusive on an interval, and closed interval is inclusive. I'm actually not sure. approximation function by its tangent line at a point x equals a. It's used to simplify calculations and analyze behavior of complex functions by treating them as linear at that point. Okay, that's reasonable. How does the tangent line and the secant line relate to the mean value theorem? It is the mean value theorem. So it states that there is a derivable point on the function between points A and B that make up a secant line, right? So on this function, there is a tangent line that is parallel to the secant line. Okay, I just answered that. Oh, okay. So we'll just go ahead. Express areas of the curve as limits. So as the amount of divisions we make under the curve approaches infinity, then we, when it's infinity, it's an exact, it's reasonable to say it's exactly it. So, oh, okay. So, okay, I'm just gonna go there. Second order derivative. So this is the rate of change of the slope. At a given point. So the upper limit, or the, so it's the little S guy, and there's like one on the top left and one on the bottom right, or I guess it's top right or top right and bottom right. The lower limit and the upper. So, okay, so I didn't get that they're all on one side and the upper limit is in the upper position, which is reasonable. Okay, the closed is square brackets, open is parentheses. This is a piecewise function. It's the E, yeah, and the sigma. Okay, piecewise function is where different functions are applied for different areas within the input domain. Yeah. Okay, local extrema. So first you find critical points by figuring out where the first order derivative is 0. And then from those critical points, you take the second order derivative and plug those in. And then if it's greater than 0, then it's a local minimum. And if it's less than 0, then it's a local maximum. Greater than 0, local minimum. Yep. Okay, perfect. This is where you approximate a function by using the tangent, or let's see, yeah, the instantaneous slope. It's tangent line, yep. Okay. Have that one as well. Okay, sweet. Okay, so we merely reviewed today, but it's still good. I was thinking about whether or not I would stream, but I think it's good to have the habit. So perfect. So I think we are good for there today. So we just reviewed what we did last time, and then we'll just kind of continue here. I'd like to get these completed fairly quickly, and so we'll try to zoom through them. But that is everything.